In this lesson, we're going to be talking about the TCP headers. So much like IP that has a set of headers, TCP also has a set of headers that serve different functions more specific to the needs of the Transmission Control Protocol, or TCP. So let's take a look at these headers. Starting off at the very top, we've got a source port here. And again, like always with Wireshark, when I select a particular field from the packet or the datagram, then I'm going to see the bytes highlighted in the raw output at the bottom here. So you can see I've highlighted the source port, and we can see the 2 bytes here that are used for the source port. So in this case, we've got a source port of 50,443. Our destination port is 443. In this case, Wireshark has done the nice thing of indicating that that's HTTPS, which is secure HTTP. Now, the next thing that we've got is we've got a sequence number, and the sequence number is used for a couple of things. If the SYN bit or the synchronized bit is set, this is the initial sequence number. Otherwise, this is just the sequence number that has to do with getting the packets in the right order when they get to the destination. So the sequence number is going to be about getting the packets sequenced, of course. So I get packets 1, 2, 3, 4, for example. If they arrive 2, 4, 3, 1, then the receiving end can put them back into the correct order based on the sequence number. So acknowledgments, when they are received, are actually to a particular sequence number, so that the sending end can say, yes, I sent this packet with this particular sequence number, and I've received an acknowledgement for that particular sequence number. Therefore, I know that that packet was received at the other end. I don't have to worry about sending it again. That's what the sequence number is used for. As I mentioned, the acknowledgement number is used to acknowledge a particular sequence number. And if the ACK bit is set, then the acknowledgement number is the next sequence number expected. The sequence number and the acknowledgement number are really tied together in terms of making sure that packets get from point A to point B, and we can make sure that they've been received, and we just check them off saying, yes, it was sent, and yes, the other side received it. The next field here is a header length, and sometimes that's called the data offset, meaning the data offset is the offset within the packet where the data starts. But this is really the size of the TCP header. And this is in 32-bit words. So we can see here the value is B0. That tells us that we've got 44 bytes that are being used for the header. So the header length is 44 bytes. The next thing that we've got is the flags, and there are a number of flags. The really important ones that we're going to be talking about has to do with really the ones below this urgent flag here. This one is reserved. The nonce and congestion window and ECN you'll see used less likely, but these others tend to be pretty important. The urgent flag has to do with urgent data. Urgent data would get received more quickly. As I mentioned previously, the acknowledgement flag says, yes, I'm acknowledging something that you have sent. The push flag is about making sure that whatever data is received is pushed directly up to the application. It's not left sitting in a buffer. So if you set the push flag, the buffer is going to immediately get cleared and sent off to the application rather than just sitting there accumulating until the application may come to get the buffer, or whether we're waiting until a certain number of bytes are read before we send the buffer up to the application. The push flag really makes sure that the data gets sent up immediately. The reset flag has to do with resetting connections. And if we get a message, for example, that we're not expecting, we would reply to it with a reset. The synchronize flag has to do with initializing connections. So I would send a message with a synchronize flag set if I wanted to start a connection with another endpoint. Now, the synchronize flag is really tied in very closely with the three-way handshake that is particular to TCP, and we'll talk about the three-way handshake in a subsequent lesson. But that's what the synchronize flag is for. Now, the fin flag is kind of the opposite of the synchronize flag. The fin flag has to do with ending connections. So fin for finish. So we're closing a connection if we're using the fin flag. Now we have a window size value, and the window size is really the number of bytes that can be sent out without receiving an acknowledgement back. So I could send 65,000 bytes in data without getting an acknowledgement back, which allows me to go pretty quickly. So I can just throw a bunch of data out onto the wire and just keep sending it up until either I get an acknowledgement, in which case I can send some more, or I hit this window size, meaning I would stop and wait for an acknowledgement. And if I didn't get an acknowledgement within a certain time period, I'd start doing retransmits. So now I have the checksum field, and the checksum is pretty much what it says. The checksum is just the checksum of the header here. The checksum says either something's been altered or nothing's been altered based on the calculation of the checksum value. Then we have a series of options here. We've got maximum segment size, a few no operations, window scale, timestamps, TCP SAC permitted, and end of option list. So these are all options, and frankly, they're optional to the messages. The primary TCP headers are the ones that are above the options, and those are the ones you're going to see in every packet. So that's the set of headers and the uses for those different headers and what they all mean. And as I said, you're going to see those headers in any TCP packet. Just based on this, you would be able to decipher what's going on with this particular message and where it is in a particular communication stream based on how these different header fields are set.